So this video is about the derivative as a function. So basically think about a function being some equation. You can plug in values of x to get different outputs of y and so forth. So it's a function. Plug in values of x to get outputs for y. So we're going to find the derivative as a function. So we look at this curve. Let's say this curve is called f of x. Make it blue. This is f of x curve here. And if I wanted to find the derivative of it, I'm looking for f prime of x. So if you think about that, basically at every point you have a different slope. Like if I chose this point, I have a slope because I got a tangent line at that place. If I chose this point, I got a different slope because I got a tangent line at that place. If I chose this point here where it maximizes, I got a new slope. And all around there, I got different tangent lines. They all have different slopes. They're kind of changing as you go down. So I got a tangent line here, I got a tangent line here, and at this place I got a tangent line, and it goes around. If I looked at it over on this side, all these lines look like they have positive slopes because they're rising as you go to the right. This line look have a slope of about 0 because it's horizontal. All these lines would have slopes of negative numbers. And then a 0 again, you got positive slope, then you're going to have negative slopes again. Then you got a 0, then you got positive slopes again, and you got another 0, and more negative slopes to the very end there. Assuming this graph does this at the end, if I remember correctly when I created it. So anyway, so you got all these slopes where you got positive sections. I'll just make a plus sign. So you got positive slopes here, you got negative slopes there, and it's changing all around. So it's negative slope. And it's constantly changing as we go. So we created a function using each one of those slopes. That would be f prime of x, because f prime of x rests on the slope of that function at any given point, and you could find the slope at any given point once you have an equation, whatever, to represent that. This time we're not going to create equations. We're just going to create what the curve should look like, so the function should look like, using the data we have here. So let's do it. All right, so I'm going to make my background white, because I'm going to do a lot of writing here. So, 1 second. For that matter, let's start looking at this from the beginning. So, what I'm looking for is this is f of x, and I'm looking for f prime of x. I'm looking for all the points I can cover with this graph, f prime of x. So let's start here. I'm going to say this right here is at -9. That's -5, -6, -7, -8, -9. So at -9 here, I would choose this point is about right there, and I want to find a slope there. So I'm going to get a tangent line there as best I can. So if I looked at this, if I made that tangent line, this is a slope of about, if you look at where it goes over about 1. I would say it goes about 1.8 over, and then it goes up 1, 2, 3, 4, 5, 6. So it goes up 6. So the slope at 9, slope at x equals 9 is about positive 6 over positive 1.8, whatever that decimal is. We'll find out what that is now. This is about 3.3. And it's just an estimation. We just estimate it by kind of using a picture. Some slopes make an eyeball and kind of guess at what that slope is. But it's estimation. So the slope at 9 equals this. If the slope at 9 equals that, that means f prime of 9 is about that. Because the slope, f prime means slope. So f prime of 9 is about 3.3. And I could choose some other points. I'm going to choose this point because it's really easy to find because it's 0. So this number looks to be -6, -7, -8. So f prime at -8, I know that's 0, exactly. And the 0 is really easy to find. So I'm going to pick another one first, though. This is -6, -7. If I tried -7, if I found a slope at that place where it's -7, I could draw a tangent line there at -7 and kind of take a guess of what that slope probably is. So if I looked at that, if I started here, this goes over and up So it looks like it goes over about, this is about 2.1. There's 1, 2, maybe about 2.1 it goes over, and then it goes up 1, 2, 3, 4, maybe a half. So it's about 4.5. And if you look at this, if I start from here, I went over to the right and I went upwards. This should be a negative slope though. So if I start from this place, it would be to the left and up. So we would say the rise f of -7, my rise is 4.5, and from here I went to the left, so -2.1. So that's about -2.1 roughly. And for that map, I got enough of those for now. I'm going to find these easy ones, the zeros. I know at f prime of 5, slope should be 0. Got another 0 here. That's at 1, 2. So I know f prime of -2 is 0. F prime of 0 is 0, because that's what 0 is. This is 1, 2. So f prime of 2 should also be 0. And just for good measure, I might choose one more slope over there. So this is at 4. So if I chose this point where it crosses at 4 is right there. So if I found the slope there is roughly, if I started here, went down and over, this looks like it went over 1, 2, 3 to the left, and went up 1, 2, 3. So I know at f prime of 3, it should be rise over run. So 3 over -3, which is -1. So I got enough points to come up with my derivative. So I'm going to use all these values to plot what the derivative function look like. I'm going to erase all this. I'm going to move the answers over in this corner here, because I'm going to put my derivative beneath. So 1 second. All right, so basically I'm going to treat all these as ordered pairs, right? So at -9, output's 3.3. So I'm going to go over to -9, output's 3.3. That's around here, roughly. At -8, output's 0. So at -8, 6, 7, 8, output's 0. At -7, output's -2.1. So this is -7, -2.1 is somewhere around there. At, this should be -5, output 0. And then at -2, 4, 3, 2. At -2, output 0. At 0 to output 0. At +2, output 0. At 3, it should be -1. So we connected these dots. It looks something like this. Went up, goes up through, comes back down through, comes back down, up through, and then back down, and so forth. So the derivative of that function should look something like this. Again, this is estimation, but that's a good estimation of what the derivative of that function would be from one number to the next. So this is f prime of x as a function, what it should look like. All right, moving on. But before I leave, I should mention this. Notice that up to this number, and this number is where x was -8. Up until where x is -8, the slope was rising. It's a positive slope because it's rising. So notice up to -8 in the derivative function, the curve is above the x-axis, so it's in the positive section for x. And then in between -8 and this is at -5, all these slopes should have been negative because all these slopes are falling, right? So in between -8 and -5, notice how the graph is beneath the x-axis because all those have negative values. And then at 5 is 0, so the x crosses at 0 because that's when the slope is 0 again. The slope comes 0 again here at -2. So notice that, but in between there it's positive. So notice that between -5 and -2, the slope is above the x-axis, so those are positive numbers for x. And then between -2 and 0, it drops again, so it becomes negative slopes. So those are beneath. So that's a good way of making sure you graph the derivative properly, if you can look at what the sign, the slopes you have, and make sure that's above, beneath, or zeros on your derivative curve. Anyway, that's all I have. Moving on. All right, in the previous lesson, we learned if we want to find f prime of a is some specific number, some specific coordinate, we could plug in a and we could find the equation for it. Today, though, we want to find f prime of x, where x could be any number. So the formula is basically the same, but we change a to x. So this represents the derivative at any given value of x. So it's basically the same as that one, but now we're not looking at a specific point, we're looking at any point for x. So we're going to use that formula to find derivatives of equations as a function. All right, going on. All right, so the example says find the derivative of this function. We can use definition of derivative with x plugged in for a. So f prime is equal to this limit. And if we plug in f of x plus h into that function, we should get, well, if f of x equals x cubed subtract x, then f of x plus h should be f of x plus h. And that should be x plus h cubed subtract x plus h. And that's a formula for expanding this. So I won't bother cubing it. I'll just follow the formula. So that should be x cubed plus 3x squared h plus 3xh squared plus h cubed subtract x. Well, let's go subtract it. It should be subtract x subtract h. That's going to be the first part of the function. So this long expression replaces this piece of the function. So let's replace it. All right, I had to tighten this up a bit. But it's going to be this whole thing, subtract f of x. Let's go up and replace f of x. That means subtract x cubed subtract x. And that's over h. Now I'm going to need more space. I'm going to have to erase all of this stuff to show you how I got there. But I'm about to erase all this stuff beneath here in green. Actually, I'm going to erase this whole screen so I can bring this piece upwards. So if you need anything, I will copy it now. All right, so for this numerator, I can distribute -1 into both of those. I can rewrite this whole equation as this. So from there, we're going to look for like terms. So you might notice that x cubed and negative x cubed cancel, and negative x and positive x cancels. So this is what we have now. So this is what we have. Notice all these have h, which is wonderful because I can factor out an h and simplify that to be this. All right. So this is perfect because now I cancel out my h's. They become 1s. And now you don't have an h in the bottom. It should be undefined. We plug in 0 for h now. So my new expression should be this. The limit as h approaches 0 of this function. Now as h goes to 0, I plug in 0 for h. This becomes 0. That becomes 0. So it just becomes 3x squared subtract 1. So that means that f prime as a function is equal to 3x squared subtract 1. So that's the derivative of the original function. So if f of x was x to the third subtract x, f prime of x is equal to 3x squared subtract 1. So we found the derivative and made the derivative of a function. If I wanted to graph this function, I would just plug in numbers for x. I get a curve that will give me the slope at any given point in my original function. So this is really useful because if I wanted to find the slope at any point, I don't have to guess. I can plug in any value of x that is in its domain and get an output that will give you the slope at any point in the original function. So that's why it's useful to know the derivative as a function, so we can actually find out the slope at any given point in that function. All right, let's talk about the graphs of those functions. All right, if you need any of this as a note, I'll copy it. I'm about to erase your screen. All right, this was f of x. This function, if I wanted to graph it, I could probably factor it first, and I'd see the zeros, and I can use those zeros to come up with the graph. So then my zeros are 0, -1, and +1 in f of x. So if I graph that, I know it should look like this. I understand the end behavior and so forth, so I understand it should look something like that. This function is quadratic, so if I want to graph it, I can use the table of values or just think about what that function looks like. So I would try to find the zeros first. I would try to find the zeros first and then come up with a curve for it. So if I want to find the zeros, I would set that equal to 0 and then solve it for x. So 1 equals 3x squared. 1/3 equals x squared. So x equals positive negative square root of a third, which is about 0.5. Well, 0.58. So if I graph that, 0.58, positive negative 0.58, it should be a parabola. It looks like this. And this is the graph f prime of x.